So we are looking at note page 250 to 251, looking at the precision and accuracy of our data. In the realms of science, the term precision and accuracy reflect different ideas about data that is collected. Accurate data is when your data, or my measured data is the same or close to the accepted value that scientists had established a long time ago. Whereas precise data represents the consistency of the measurements. Every time you or I collect data for this experiment, are our results the same or similar or all over the place? So one way of looking at accuracy and precision is looking at these targets. So the target. So I'm going to put an X here, and that X is what is known as the bullseye, and the bullseye represents the actual or accepted value. So that's what we are striving for. This is something that scientists before us have established, right? Whereas these other marks on the target, this would be the student data. So when you compare each of the students' data to the bullseye, we see that for the most part, they are not similar or close to the bullseye or the accepted value. So the student data overall would have low accuracy, not similar or the same. And then when you compare the students' data points, they are all over the target. So that means that there is a lack of consistency in this data, so low precision. If we move across to this target, where here's the bullseye, and you take a look at the student's data is not the same or similar to the accepted value. It's still pretty far away. But this time, take a look. The student's data is clustered or grouped all in one area on the target. So there is consistency in this data. And usually when this happens, this could indicate ideas low accuracy but high precision. It could indicate that there might be an issue with the equipment. So maybe the equipment is out of calibration and needs to be fixed. Or the student is starting to use the piece of equipment and is more consistent in how they are using it, but however, their technique or skill is still being developed. So I'm going to just write tech/skill. Other things that we tend to see as we're learning to collect data is that here's our bullseye, and what we start to see is our collected data is much closer to or similar to the accepted value, but it's still a little bit all over the place. So we have higher accuracy, but still pretty low precision. And then as we get working in the lab and we're doing it with more practice, like any other skill, we start to see where we start to collect data that is very similar to the accepted value, and our precision increases because every trial we end up with similar results. And so high accuracy, high precision is what we're aiming to develop skill-wise by the end of the school year. But when you are talking about your data in the lab, I'm not going to ask you, nor is it effective to draw a target to explain the precision and accuracy of your data. So what we do is we have a calculation that is known as percent error. And so it's a mathematical relationship where one part of it is referred to as the measured value. And the measured value, you will see me short form it in the notes as MV, and an accepted value, which I will refer to as the AV. So it is an absolute difference between what you or I as the student measure and collect compared to the accepted value, the established value by scientists. So it's an absolute difference. And because it's an absolute difference, if you put this in the calculator and the difference turns out to be a negative, we ignore the negative sign. So an absolute difference where we make the difference a positive value. The math is pretty easy. Sometimes the hard part is identifying what information represents the measured value versus the accepted value. So common terms that we tend to see in our class that will identify a value as being the accepted, obviously the accepted, but it could also be referred to as the actual value, the true value. Um, if we look it up in a reference journal, like your reference table, so it could be the referenced value, what scientists have established. Let's see what else. It could be the standard value. It could be the recognized. So normal human body temperature, the recognized value is 98.6 degrees Fahrenheit. So most people have a natural body temperature similar to that. So that's what we recognize as the normal or healthy body temperature. So the recognized value. Where is the measured value? So if any information is given to you where it's referred to as something like the student, what the student did. So the student collected. So here we go. So terms, it could be the student measured, the student collected, the student calculated, the student observed, the student determined, the student obtained, right? So if it's put anything that the student did would be a big clue that that's the measured value. So let's take one look at an example of a percent error calculation. So here we go. So one of the things is I always like to annotate in the question. So during an experiment, the density of aluminum is calculated. So I see this word is calculated. And when I see the wording is calculated, right, that falls under a measured value. And what it's calculated to be is this number. So I'm going to understand that this number is a measured value. And it was determined at room temperature. Now it simply says determine. So that's our job, the percent error. And I don't see any other numbers being provided. So first thing I'm going to do is I'm going to write down my mathematical relationship. So it's the measured value minus the accepted, and it's an absolute difference, divided by the absolute value times 100%. So I know when I read through the problem, I have the measured value, and there it is. But in order to solve this problem, I also need an actual value. So here's one of the things. If we need an actual value, but it's not provided anywhere in the given information, then it is understood that we know where to look and find it. So you have to look at your table S to find the actual value, which in this case is the density of aluminum. So the actual density of aluminum. So density of aluminum, and when you look it up on this table, table S, it is written as 2.70, and up near the top where it says density, it'll read grams per centimeters cubed. So now I know my measured and my accepted, and so now I'm going to do my correct numerical setup. So Don't get lazy. Always do your correct numerical setup so you always earn max number of points possible. So where it says MV, I'm going to put in my measured value. So 2.51 grams per centimeters cubed minus my actual value, which is 2.70 grams per centimeters cubed according to our reference table. That difference is then divided by 2.70 grams per centimeters cubed. And then I need to multiply that quotient by 100% to change it into a percentage. And so when you put this into your calculator, you get something like this, 7.03870,387. I think it kind of repeats out like that. So we haven't talked much about significant figures, but the measured quantity contains 3 sig figs. So our percentage should probably represent that. So we can only keep 3 of those digits. So here are those 3 digits, but that digit to the right of the 3 will make it round up. So the best final answer would be 7.04%. Your job is now to do the you do and read through it, annotate the question, show your correct numerical setup and final calculated answer, and then check with me to make sure you did the calculation correctly.